Hello dear students, Assalamu alaikum. I hope you will be fine. My name is Engineer Mirza. I am lecturer in Department of Technology, Sarad University of Science and Information Technology, Peshawar. As I am teaching you the subject Fluid Mechanics, today is your lecture number 11. In lecture number 11, we will study about practical applications of Bernoulli's equation. So, what are the practical applications of Bernoulli's equation? The Bernoulli's equation or theorem is the basic equation which has the widest application in hydraulics and applied hydraulics. Since this equation is applied for the derivation of many formulas, therefore its clear understanding is essential. Though the Bernoulli's equation has a number of practical applications, yet in this chapter we will discuss its application on the following hydraulic devices. Number 1 is Venturi Meter, number 2 is orifice meter, number 3 is pitot tube. These are the hydraulic devices which are based on the practical application of Bernoulli's equation. So coming to Venturimeter, a Venturimeter is an apparatus for finding out the discharge of a liquid flowing in a pipe. A Venturimeter in its simplest form consists of the following three parts. The first part is known as the Convergent Cone, the second one is the throat, and the third one is the Divergent Cone. So the Venturimeter consists of these three parts. The Convergent Cone it is a short pipe which converges from a diameter d1 to a smaller diameter d2. The convergent cone is also known as inlet of the Venturimeter. The slope of the converging sides is between 1 in 4 or 1 in 5 as shown in figure 7.7. As you can see, this is the convergent cone. The second one is the throat. It is a small portion of circular pipe in which the diameter d2 is kept constant as shown in figure 7.7. This is the known as the throat of the Venturimeter. While the third part is the divergent cone. It is a pipe which diverges from a diameter d2 to a larger diameter d1. The divergent cone is also known as outlet of the Venturimeter, and the length of the divergent cone is about 3 to 4 times than that of the convergent cone as shown in figure 7.7. In fact 7.8. This is the total length. This is the divergent, and its length is about 3 to 4 times of the divergent convergent cone. A little consideration will show that while flowing through the liquid, while flowing through the Venturimeter, when accelerated between the section 1 and 2, while flowing through the convergent cone, as a result of the acceleration, the velocity of the liquid at section 2, that is at the throat, becomes higher than that at section 1, and this increase in velocity results in considerably decreasing the pressure at section 2. If the pressure head at the throat falls below the separation head, which is 2.5 meters of water, then there will be a tendency of separation of the liquid flow. In order to avoid the tendency of separation at throat, there is always a fixed ratio of the diameter of the throat and the pipe, that is d2 divided by d1. This ratio varies from 1/4 to 3/4, but the most suitable value is 1/3 to 1/2. The liquid, while flowing through the Venturimeter, when the liquid is decelerated or retarded between the section 2 and 3, that is while flowing through the divergent cone, as a result of this retardation, the velocity of liquid decreases, which consequently increases the pressure. So as the velocity of the liquid decreases, as a result of this, the pressure of the liquid increases, and if the pressure is rapidly recovered, then there is every possibility of stream of liquid to break away from the walls of the meter due to the boundary layer effects. In order to avoid the tendency of breaking away the stream of liquid, the divergent cone is made sufficiently longer. Another reason for making the divergent cone is longer is to minimize the frictional losses. Due to these reasons, The divergent cone is 3 to 4 times longer than convergent cone as shown in figure 7.7. Now, as we all know that Venturimeter is used to find the discharge through a pipe. So how the discharge is measured through a Venturimeter? For this, consider a Venturimeter through which the liquid is flowing as shown in figure. Let P1 is the pressure at section 1 and V1 is the velocity of water at section 1. Similarly, D1 is the datum head at section 1 and A1 is the area of Venturimeter at section 1. And P2, V2, AZ2, A2 are the corresponding values at section 2. Now, apply Bernoulli's equation at section 1 and 2, that is Z1 plus V1 square divided by 2G plus P1 divided by omega is equal to Z2 plus V2 square divided by 2G plus P2 divided by omega. And now let's pass our datum line through the axis of the Venturimeter as shown in figure 7.8. As you can see, this is the center of the pipe, and let the datum line passes through the center of the pipe, center of the Venturimeter. So as a result, Z1 and Z2 will be equal to 0. So equation 1 comes out to be V1 square divided by 2G plus P1 divided by omega is equal to V2 square divided by 2G plus P2 divided by omega. Rearrange this equation and you will get this equation P1 over omega minus P2 over omega. Take this P2 over omega on the other side, it will become minus, and take this V1 square over 2G on the other side, it will become minus. So we get in equation number 2, that is P1 over omega minus P2 over omega equal to V2 square divided by 2G minus V1 square divided by 2G. Now, since the discharge at section 1 and 2 is continuous, therefore A1 V1 equal to A2 V2 from the equation of continuity. From this we get V1 equal to A2 V2 divided by A1. Take square on both sides, we will get V1 square equal to A2 square V2 square divided by A1 square. Now put the value of V1 square in equation number 2, which is this equation. Put the value of V2 here. So V1. Put the value of V1 here. So you will get P1 over omega minus P2 over omega equal to V2 square divided by 2G minus A2 square divided by A1 square into V2 square divided by 2G. That is equal to V2 square divided by 2G into 1 minus A2 square divided by A1 square, and that is equal to V2 square divided by 2G into A1 square minus A2 square divided by A1 square. Now we know that P1 over omega minus P2 over omega is the difference between the pressure head at section 1 and 2. So when the pipe is horizontal, the difference of represent the Venturi head, and the Venturi head is denoted by H. So replace P1 divided by omega minus P2 divided by omega with H. So we get H is equal to V2 square divided by 2G into A1 square minus A2 square divided by A1 square. Now rearrange this, we will get V2 square equal to 2GH into A1 square divided by A1 square minus A2 square. Take under root on both sides, you will get V2 equal to under the root 2GH A1 divided by under the root A1 square minus A2 square. Now we know that the discharge through a Venturimeter Q is equal to coefficient of Venturimeter into A2 V2. This is not Q2, this is A2. So put the value of V2 here. So you will get the equation of discharge through a Venturimeter Q is equal to C, which is the coefficient of Venturimeter, into A2 V2, that is equal to CA1 A2 divided by under the root A1 square minus A2 square under the root 2GH. So this is the equation which is used for finding discharge through a Venturimeter. Here is a small note. The Venturi head H in the above equation has been taken in terms of the liquid head, but in actual practice this head is given as the mercury head. So in such a case, the mercury head should be converted into the liquid head. If the given liquid is water, the mercury head can be converted into water head by simply multiplying the mercury head by the specific gravity of mercury minus the specific gravity of water, that is 13.6 minus 1 equal to 12.6. Sometimes an oil is being discharged through the Venturimeter, In such a case, the Venturi head should be taken in terms of the oil head, that is H is equal to 13.6 minus omega divided by omega into head of mercury. Here 13.6 is the specific gravity of mercury and omega is the EU specific weight of oil. And this is the end of today's lecture.